So we were watching a Hawking's lecture on gravity, the weakest force, but what makes it so effective all across the universe and so powerful, even though it is the weakest, so to speak. But to know that, we have to first understand things like neutron stars. Let me talk about them first. So neutron stars are what? They are incredibly dense, remnants of supermassive stars that have exploded as supernovae. Stars' evolution and ultimate fate depend on large part on its mass. So all supermassive stars, stars with an initial mass that is greater than about 8 times that of our sun, have the capacity to eventually become neutron stars. When a supermassive star begins to die, it forms a red supergiant. After that, these stars explode and they either evolve into white dwarfs or become supernovae. So it depends whether they explode further to become a supernova or nova or white dwarf, which is like just a very hot, dense particle, so to speak. If what remains of the core of the star after the supernova explosion has a mass less than that, about 3 times that of the sun's mass, then it forms into a neutron star. So even after there is the supernova explosion, uske baad, after that, if the mass that is remaining is less than 3 times that of our sun's mass, only then it becomes a neutron star. Okay. If the remnant is more massive, it will collapse into a black hole. Can you imagine? So a star has to be massive to have a supernova, first of all, and then even more massive than a normal star when it ultimately needs to become a black hole. Otherwise, it just becomes a neutron star, which is not to be taken lightly, also. What is a neutron star? So, they are fantastically dense, these neutron stars, and they have a mass that is greater than that of the entire sun. On its own, right now, the neutron star has a mass which has greater than our sun, but the radius is only about 10 kilometers, so like your workplace to your home if you're in India. That is the size of the neutron star, but it is heavier than the sun. Can you imagine that kind of density packed in such a small area, small volume? What will that do? Let's find out, or you can guess. So, a single teaspoon of a neutron star would have a mass of about a trillion kilograms. What is trillion? Just find out, okay? Google. I think it's bigger than billion. Anyway, so a single teaspoon of a neutron star. This is my tea. It should have a spoon. Let's pretend this is a spoon. A single teaspoon of a neutron star will weigh more than what? A trillion kilograms. Can you imagine? What is this density? So anyway, neutron stars are so named because they are composed primarily of neutrons, as most of the protons. So neutron star, as the name suggests, is made up of neutrons. But where did they all come from? So as you know, usually in a star, what is there? When there is a living, thriving star, what does it contain? It contains a lot of hydrogen atoms. A lot of means billion. I don't know how many hydrogen atoms. And somehow there is this nuclear fusion reaction going on over there because of the intense pressures and temperatures. What happens is hydrogen is what? It's ultimately a proton, right? Or a neutron. So it's like proton slash neutron, or just, it can also be just neutrons, right? So a neutron star is what? It doesn't contain protons. It only contains neutrons. So where did all the electrons go? Where did all the protons go? They There was, let's find out. So what happens is neutron stars are so named because they are composed primarily of neutrons, as most of the protons and electrons will have combined to form neutrons under the incredibly dense conditions. Even though they do not actively generate heat through nuclear fusion, neutron stars are incredibly hot, with temperatures far exceeding those of regular stars. So what they are saying is, it's not that a neutron star is not hot. It is, but it's not because of nuclear fusion. And the temperatures at the surface can exceed more than normal stars. So how much is our sun? Our sun is like 6000 Kelvin or something. So much more than that is a neutron star, which is what? Just 10 kilometers in diameter, and it packs so much mass, like I said, that one teaspoon has trillions of has trillions of kilograms packed in it. So of course, I mean, we can assume that such an object with such a high density will emit some sort of heat. It's not from a nuclear reaction. What more do we know? So in 1997, when my brother was born, Hubble provided the first direct look. Hubble is that telescope. You should know this. Anyway, so it's named after a scientist, Edwin Hubble. Anyway, first direct look in visible light at an isolated neutron star. So we were able to see with our naked, we could have seen the image with our naked eye, is what they are saying. It was in visible light, not in any other spectrum. So the star was clearly making itself visible in visible light spectrum. That's interesting, right? Because normally there are some celestial bodies which are only emitting, say, X-rays or gamma rays or even just gravitational waves. So what do you think emits just gravitational waves and nothing else? It's a small quiz. I'll tell you the answer at the end of this video. So okay, yeah. So it was observed in 1997 by Hubble with visible light as an isolated neutron star. The telescope's results showed that the star is very hot. It is 6,70,000 degrees Celsius at the surface. much more, like orders of magnitude more than the sun's temperature at the surface, and can be no larger than 28 kilometers across, matlab the diameter, right? These results prove that the object must be a neutron star. Why? Because such heat is getting emanated from the surface of a celestial body, and it is packed only within like 28 kilometers of diameter. So the scientists thought this is a neutron star because no other known type of object can be this hot, this small, and dim. Anyway. In 2017, the telescope also observed for the first time that the source of gravitational waves created by the merger of two neutron stars. Really? So they are saying that when two neutron stars merge, it produces gravitational waves. See, you would think that this is obvious. Why? Because neutron stars are incredibly dense, hence incredibly massive, and something which has a lot of mass will have some sort of gravitational force coming out of it, right? So when two such objects combine, they produce gravitational waves. What else? So when something like this happens, when two very massive objects, gravitationally like significant objects combine, they not only emit gravitational waves, but they also emit or eject heavy elements such as gold and platinum into space. This event also provided the strongest evidence to date that short duration gamma ray bursts are caused by mergers of neutron stars. Prior to this result, when this platinum or gold is ejected out of a celestial event, it is called a kilonova. So I think it's called kilonova because kilo stands for weight, like, and gold and platinum are heavy elements, right? And kilos are usually it's a unit to measure higher weights, not in grams or nanograms or such things. So kilonova. And so short duration gamma ray bursts are caused by mergers of neutron stars. Prior to this result, connecting kilonovae and short gamma ray bursts to neutron star mergers had been difficult. But the multitude of detailed observations following the detection of gravitational wave event, including those by Hubble, finally verified these connections. Anyway, so in May 2020, the light from the glow of a kilonova caused by the merger of two neutron stars reached Earth. Right in the middle of global lockdowns, one kilonova light reached a planet. And then this was used by Hubble to study the explosion's aftermath and the host galaxy, whoever hosted these two neutron stars, and found that the near infrared emission, infrared is what? People relate infrared to heat because it's not visible light. It is has less frequency or more wavelength than visible light. So it is they expected very less infrared to come out of this event, but actually it was 10 times brighter than predicted, which means it was a lot of heat emitted. These results challenged the conventional theories of what happens in the aftermath of a short gamma ray burst. Anyway, that's it. That's it for today's video. And the answer to that question is dark matter. So that's it.